Welcome to Africa Tech Academy. Today we'll be starting with Unit 4, and this is the last unit you need to cover before your end of semester examination, which is magnetic circuits. So with magnetic circuits today we'll be learning how to calculate the reluctance, flux density, magnetic field intensity, and force or MFF. So sometimes the force, they can tell you to calculate for force. Today we'll look at examples on how to calculate all these quantities in a circuit. So without wasting much time, let us get started. Our first example says a mill steel has a cross-sectional area of 800 millimeters square and a mean circumference of 400 millimeters. It has a coil of 500 turns wound around uniformly around it. Calculate the reluctance of the ring. B. The current required to produce a flux of 700 microweber in the ring if the relative permeability is 400. So they've given us some important parameters, so we need to convert them to the right unit in order to use it. So first of all, they've given us our cross-sectional area, which is 800 millimeter square. So you might see that I've already converted it. Let me show you. The 800, the millimeter square here is simply equals to mm square. So that means the millimeter is square. So it now becomes 10 minus 3 all square m. So that is how I did, and I got my 800 times 10 minus 6. So that is how we do it. Then the area is always measured in meter square, so you have to leave your answer in meter square. So that's why you have to convert it. This is the tricky part about these questions. Then let us also convert our length. Length is measured in meters, so 400 millimeters. So you convert it to meters, so it's now in meters. And the number of turns is 500 turns, so you just write it down. Then the first thing you need to do, we have to find the reluctance, and this is a formula work. They've already given us the formula for reluctance, and this is the formula for reluctance. Is the length all over u naught ur and multiplying by the area. U naught is a constant value, ur is the 400 that was given to us, and the length is given to us, area is given to us, so we just have to change it back into the formula. So changing everything back into the formula, we have our 400. This was our length, 400, and this is our constant u naught, and this is r, the ur, relative permeability. Then the area, which is 800 times 10 raised to the power minus 6. After doing all this mathematics, and you get your reluctance S as 99471.397 AT over Webers. So after getting this answer, we've now calculated for A, the reluctance of the ring. We need to now calculate the current required to produce a flux of 700 microwebers. So to calculate the current, or we have to first of all find the magnetomotive force, which is also known as MMF or force. And we can find the magnetomotive force by using these two formulas. Either when we know the flux and the reluctance, or the number of turns and the current. In this case, we know the flux and we know the reluctance, so we can use the first one. So we have our F times our flux. Our flux was 700 microwebers. So that is 700 times 10 raised to the power minus 6. So finding that is 700 times 10 minus 6 times the reluctance. The reluctance X was 99 this. So doing that, we get an answer of 696.30380. After finding the force, that means we now know our magnetomotive force or our MMF. So finding that, we now need to find the current. To find the current, we need to make I the subject in this equation. So I here is now equals to the force divided by the number of turns. So I is force over number of turns, which is this. Doing that, we get our current as 1.392 amps. So the current that will be flowing through the ring will be 1.392 amps. So this is how we simply calculate these kind of questions. It's just a formula. You have to analyze it well, into the appropriate one. So let us take our next example and we'll see how it goes. Okay, so our next question says a coil of 2000 turns is wound uniformly over a wooden ring having a mean circumference of 500 mm and a uniform cross-sectional area of 500 mm square. If the current through the coil is 2 amps, calculate the magnetic field intensity, flux density, flux, and magnetomotive force. So let us look at the parameters that have been given to us. The area, which is 500 millimeters square, converting it, we get this. And the cross mean circumference, which is the length, converting it, we get this. The number of turns, which is 2000, and our current, which is 2 amps. So after getting all this, we need to now find the magnetic field intensity, which is represented as H. So magnetic field intensity is simply the force over the length. So magnetic field intensity is the force over length, and we know that the force is also equals to the number of turns times the current. So the number of turns is 2000, then the current is 2, so we just multiply it by 2 to find the force. Then we divide it by the length. The length was this that we've already calculated. Dividing it, we get 8080 per meter. Then after finding the magnetic field intensity, we need to now find the flux density. To find the flux density, we can use two formulas to find the flux density. It's either we use this formula or we use this formula. But realize that this formula will work best for us because it's simple. This formula here, we know the magnetic field intensity already, which is and this constant, we know it already, mu naught, which is the 4 pi times 10 raised to the power minus 7. So we just multiply that by this. So calculating for the flux density is 4 pi times 10 raised to the power minus 7 times the 8000, which we get our answer as this. After getting our answer, we need to now calculate for the flux. To calculate for the flux, we use this formula. We realize that the flux here, this is the flux. The flux here, making the flux the subject to be equals to the flux density multiplied by the area. So doing that, flux density multiplying by the area, we get our answer as this. After doing that, we now need to find the current, the magnetomotive force. So to find the magnetomotive force or the force, which we've already found it here. So we said the force is equal to the number of turns times the current. The number of turns was 2000 and the current was 2. So we just multiply the number of turns by the current using this formula. Then we get our 4080. So this is how we simply calculate for the current in this circuit. The number of force, the force in this circuit. So it's just a formula work. This is the tricky part. Knowing how to convert your area and your length to the appropriate units is what is important. Our next question says, calculate the magnetomotive force required to produce a flux of 0.01 Weber across an air gap of 8 millimeter long, having an effective area of 700 centimeters square. So we have to convert all the areas to the appropriate units before we can use it in our calculation. So for the area, the 700 centimeter square, we know that centimeter square, it means what it means is that it's the cm all square, which is also equal to c square m square. So the 10 centimeter square simply means that it is 10 raised to the power minus 2 all square. So that is why how I got my 10 raised to the power minus 4. So doing that, we have to also convert the length. Converting the length to the appropriate unit, we have 10 times 10 raised to the power minus 3. And the flux, we've been given the flux. And the thing is that they are telling us that we have to calculate for the magnetomotive force. But before that, we have to calculate for the flux density. So to calculate for the flux density, it simply equals to the flux divided by the area. So flux density is equals to the flux divided by area. So we know the flux, which was 0.01, divided by the area, which was 700 times 10 raised to the power minus 4, which is equals to 0.143 Tesla. After getting our answer, we need to now calculate for the magnetic field intensity. So to calculate for the magnetic field intensity, we call our formula B is equals to U naught H. So we make H the subject. We have our B all over the U naught. So B was our flux density was 0.143 divided by 4 times, and we'll get our answer as this. After getting our answer as this, we now need to now find our magnetomotive force or our force. So we realize that when we multiply um, the the mag, magnetic field intensity by the length of the air gap, the meters will cancel out and it will be left with only 80, and we know that magnetomotive force is measured in 80, so we just multiply it, then it cancels out, then our magnetomotive force becomes this. So our final answer becomes this. But if you want to also use the other formula, you can use the other formula. You end up getting the same answer. But this is also a shortcut trick that I wanted to show you. So you can use the other formula and come and arrive at this same answer, and also leave your answer in the comment section. So thank you very much. Okay. Our question says, assume that there are no leakages and UR is equals to 1000. Right. Estimate the current required in the circuit to produce the flux density. So since they are saying we should assume that there is no leakage, meaning the A, B, and C are in series. So meaning if the same amount of flux if will flow through them. So the flux in C should be equals to the flux in A and B and C. And they've given us the values of everything we need at A and C. So here is millimeter square and millimeter squares. So and they've given us our number of turns as 2005. First of all, state that we said since they are in series, because they're saying we should assume that there are no leakages, and before because there will not be leakage, that means they are in series. So since they are in series, we see the flux in C, the flux in B, and the flux in A. So we just state it as this. The flux in C is equals to A and B. So let us calculate the flux at C because they've given us the flux density, the flux density at C. So doing that, to calculate the flux at C, we simply multiply our 0.3 times our area. So to calculate the flux at C, the area there is 150 milli. So and to also convert the area to the right hand, so now becomes 0.3 times 150 times 10 raised to the power minus 6. So doing that, we get our answer as this. After calculating the flux in C, meaning we now need to calculate the magnetomotive force, in A, and we know that the formula to calculate the magnetomotive force, F here is equals to the inductance, the flux times the reluctance. So but we have calculated, we said the flux in A is equal to the flux in C and the flux in. What we need to know is we need to calculate reluctance the reluctance for each of them, for reluctance for A, reluctance for B, and reluctance for C. So because I want to make the formula simple, the work simple, I just added the reluctance formula. So you see, reluctance is equals to, we know that reluctance S is equals to L all over U naught area. So that's why I added here. So wherever, so since I'm calculating for the magnetomotive force for A, I said Fa. So is the reluctance in C, which is also known as the reluctance in A, times the length of A divided by the UR, U naught, and area of A. So doing that, we get this value. So after getting this value, we know that the area, considering A, the area was 50 millimeter square, and the length was the length was 60 millimeter. So we multiply the 50 millimeter square, then the 60 everything, and divide, so we get our answer. Then we do the same for B. Doing for B, we get our final for FA. The magnetic force in A should be this. And doing the same thing for B we realize that our length was, what was our length? Our length was 30 millimeters square. So we bring our 30 millimeters square. These are just constant. Then divided by the area. The area was 80 millimeters square. So 80 times 10 raised to the power minus 6. Then we'll get our answer as 8.9580. Then we do the same for C. But C, they said it was complete, but we realized that C, it was not complete. We realized that C here, it was free space. So we use the UR for free space, and the UR for free space is A1, which is 1. So doing that, the UR now becomes 1 instead of the 1500. So the area was 150 times 10 raised to the power minus 6. And the length was 0.3 times 10 raised to the power minus 3. Then we just get our final answer as this. So we now know all this, the magnetic force in A, B, and C. So how do we now find the current? The current is simply equals to the force, the total force divided by the total number of turns. So we simply add all the forces together, FA, FB, FC, and divide it by the number of turns. So dividing it by the number of turns, we have 2500. That is how we finally get our answer as the current that will be flowing through, because 0.044 amps. So this is how we simply do our calculation. You realize that it's just a formula work, and we just apply the concept of series here and free space here. So there's nothing really difficult here. So kindly take your time, go through and really understand this. So thank you very much. So thank you very much for watching. Please, if you have not subscribed up to this time, please remember to subscribe, hit the bell icon and notification. So I think this is the last unit that you need to cover before your end of sem. So what I'll now be doing is that I'll just be solving questions in your reference book, so that it will really go a long way to help you. So please remember to like, share, and subscribe. And please feel free to email us or contact us when you have issues. Bye.